Hello and welcome to this video where I'm going to have a look at the Cambridge Chemistry Challenge for lower 6th, their June 2012 question paper, namely question 1. I should just clarify that I'm in no way associated with the challenge or Cambridge University, and this video is primarily designed as a walkthrough for students who have attempted this as part of their studies and preparation. With that in mind, let's begin with this part where we'll look at question 1A and B. So we can see here we're given quite a lot of information about homeopathic solutions, specifically about arsenicum album or white arsenic, which is one of the oxides of arsenic. And there's a lot of information there that we'll come back to later. For now though, let's begin by looking at question A part 1, the oxidation state of arsenic in As2O3. This is a pretty typical question for most AS or A-level papers. So hopefully we should remember that in As2O3, the oxygen here, not being part of a peroxide or bonded to fluorine, will contribute a -2 each to the oxidation number. So the total contribution to the oxidation state of this compound from oxygen is going to be equal to -6. Now overall, we can see that the compound is neutrally charged. So overall, the oxidation state is 0. That means that the arsenics must cancel out the oxygens completely, meaning that the arsenic's total oxidation state must contribute +6. So if we divide that by the number of arsenic atoms present, we should see that each arsenic has an oxidation state of +3. Now, for this next question, 1A part 2, an equation for the production of the arsenicum album, this is where we're going to refer back to the information given to us in the question. So if we look, it tells us that arsenicum album, the oxide here, is one of the products, and they also tell us the other products, and those are iron 3 oxide and sulfur dioxide. So we've got 3 products here. We're also told, somewhat obliquely, about the reactants. So we're told that we're starting with arsenopyrite, FeASS, and that this is in air. Now if we examine the products, we can see they all contain oxygen. And the oxygen's not present in any reactant that we're given a formula for, so it's probably safe to assume that the reactant coming from the air is going to be O2. So with this information, we should be able to construct an equation which we'll then need to balance. So using the information that we've been provided with, we should be able to construct an equation like the one written here, where we have the arsenopyrite reacting with atmospheric oxygen to produce the arsenic oxide, the arsenicum album, the iron 3 oxide, Fe2O3, and sulfur dioxide. Now, we're going to need to balance this equation, and the first port should be to see that we have 2 arsenic atoms and 2 iron atoms in the products, and only 1 of each in the reactants. Well, that's easily rectified by popping a 2 in front here. We should then see that that's going to affect the sulfur. So we have 2 sulfur atoms now over here, and only 1 over here. So we're going to need 2 sulfur dioxides. And finally, to balance the oxygens, we should see the total contribution to the number of oxygens from the sulfur dioxide is 4. In the iron 3 oxide, we've got 3 oxygen atoms, and in the arsenicum album, we also have 3 oxygen atoms, for a total of 10 oxygen atoms in the products, which means that we're going to need 5 O2 in the reactants to balance that out. For part B, we're given some additional information which tells us about the arsenicum album, the oxide, being moderately soluble in water, and 1 decimeter cubed of a saturated solution containing 20.6 grams. We're also told that the oxide reacts to form Asinus acid H3ASO3. And B part 1 says that all of the hydrogen atoms in this acid are in the same environment and suggest a structure for the acid. And what is the geometry around the arsenic atom? So there's a couple of things here. We need to figure out what they mean by the same environment. Well, that means that basically all of them must be in an equivalent position. There's nothing different between them. And also we're going to need to look at our periodic table. Now hopefully when we look at our periodic table, we will notice that arsenic is in group 5. And we've got 3 things or 3 groups bonded to it. So this is going to end up being a pyramidal structure. So we've got AS bonded to 3 OHs here, like this. Put a wedge bond in there, another just here. There we go. And then the geometry, I'm going to put just a belt and braces approach. It's pyramidal shape with a 107.5 degrees bond angle. Now, as for the equation, we should recall that we're starting off with the As2O3, the arsenicum album or white arsenic. We're dissolving that in water where it's going to react with the water to then go on and form Asinus acid H3AsO3. Now, what we should notice almost straight away is that we have only one arsenic atom in this product, but we have two in the reactants. So we're going to balance this by putting a 2 in front here, and then we're going to somewhere need to find 6 hydrogens. Now we should hope, and an additional number of oxygens. We should hopefully see the easiest way to do this is to put a 3 in front of our water there, and if we then count it up, we've got 2 arsenic atoms in the reactants and 2 in the products. We have 6 oxygen atoms in the reactants and 6 in the products, and we have 6 hydrogen atoms in the reactants and also 6 in the products. For this next part of the question, we're asked to calculate the concentration of the asinus acid in the solution. Now, in a saturated solution, we know that we started off with 20.6 grams of the arsenicum album. Now, I would suggest that the sensible move, therefore, is to calculate the relative formula mass of this. And using the periodic table included at the end of the paper, we should know that the arsenic has an atomic mass of 74.92. And we're going to add to that the oxygen, which has an atomic mass of 16, for a grand total of 197.84 the relative formula mass there. So what we can do then is we can work out how many moles of that we've got. We'll just work out moles in the normal way. So remember, moles is equal to mass, little m there, over formula mass. So that's going to be equal to 20.6 divided by 197.84, which we should hopefully see is equal to 0.104 moles. But then, looking at the equation we've just written, we should see that the ratio of the oxide to the acid is 1 to 2, and therefore we're going to have 0.104 times 2 moles in this solution, which is going to give us 0.208 moles per decimeter cubed. There we go. So I hope this has been helpful as a starting walkthrough. Join me again where we'll go for the next part of the question. And if you've got any further clarifications you'd like to ask for, feel free to add them into the comments.